Alright, this is the lecture for April 4th. You guys hopefully just had a delightful experience with your quiz, and I will try to get those graded and back to you as soon as possible. As you guys are watching this, I am taking a day off of work to study. And so I feel your pain, guys. I'm studying all sorts of stuff that I haven't thought about in years, and been spending a lot of time doing that, and I am a little mentally fatigued from today, and will be more so after tomorrow. So y'all need to be extra vigilant to watch out for me making mistakes in my lecture. So pay attention, because I could sneak in a mistake as a test, of course, for y'all. Not as an actual mistake, of course. At any moment, I could sneak one in. So be aware of that. And I might not even say anything about it in the video. So y'all have to be super aware. Of course, I'm just kidding, guys. I make mistakes all the time, and am particularly prone to them when I'm tired. So we're just going to move pretty quickly through lecture of 10.4 here. It's got two subsections. We're going to go through those, and then we're going to look at a couple of examples, and then we will be done here. And then you guys will have some homework for next time. We'll finish up the lecture of Chapter 10, do a little review of Chapter 10. Next time I talk to you, hopefully I will have looked at your quizzes, and we can know where everybody is and where they need to be, and so on and so forth. All right, so last time we talked about concentrations. Okay, then we talked about molality and molarity, right? That's two different ways to talk about solution concentration here. We had molality was moles of solute per solvent mass, not mass of the whole thing, but solvent mass. And that's measured in kilograms. So that should be moles per kilogram here. All right, and then molarity is moles solute per liter of solution. Okay, so that should be moles per liter. Okay, so remember that this one is much more common than that one, but they both exist. Okay, and I'll try to, no one's going to try and trick you between those two. Okay, but you do need to know the difference so that when I italicize, bold, and underline something molarity, you're not confused about which one I'm asking you to do. Okay, so that brings us to 10.4, which is compounds and aqueous solutions. Okay, so if you guys remember, earlier in the chapter, we looked at these things. And we talked about which ones were soluble and which ones were insoluble. And we talked about where that line was, right? That it had to have 0.05 moles dissolved in 1 liter of water, or it's really not soluble. And of course, there's a whole area that talks about solubility constants. And so it's not just soluble or insoluble. It's when things partially ionize and they have a solubility constant, how you calculate those things. And so, lest you believe that there's nothing else for you to learn about chemistry, there's plenty else, but we don't have the time or bandwidth really to go into that. So there's a whole range of solubility where things dissolve or not dissolve in or ionize or not ionize in water. All right, so what we're going to talk about today is ionic equations and precipitates. Okay? And that's not precipitants, it's precipitates. Like the verb is precipitate, and the thing that does the precipitating is a precipitate. Okay? All right. All right. So we have to be able to look at writing these ionic equations, and just to remind you what that looks like, flip over to page 276 here. You've got Ki. Remember, we can indicate the physical state or the phase of that. When we mix it with water, it goes to aqueous. And that's what that means. It means it's floating around in water. Okay, and remember what happens is those polar molecules come in and they boop, steal that K out of there and boop, take that I out of there. So there's actually kind of a polar molecule hanging around right here so that those don't try to find one another again. So we could sort of draw our oxygen, oxygen, hydrogen, hydrogen, and this is, remember this little guy, plus, minus. And so it's kind of got those regions on it, right, where they're polar regions. And so that minus is hanging around with this plus so that these guys don't end up coming back together like a magnet. Okay? All right, so that's what's going on. This is now in aqueous. That means it's surrounded by water molecules. Okay? And so something we need to know is that if two ionic things that seem like they should make a reaction, both are fully soluble in their solution, there is no reaction that happens. Okay? All right, so what does that look like? Okay, so let's say we did this, and I'm just making this up, so this may not be the best example. Okay, what's going to happen here? Okay, so this is soluble. That's just table salt. This is just another kind of salt. It's also soluble. All right, so this is going to have no reaction. Why? Well, if we just wrote the ionic thing, what's going to happen? This is going to become Na plus and Cl minus. This is going to be Ca2 plus and Cl minus. Right? So let's just say there is a reaction. Let's just pretend there is. Okay, what's going to happen? Let's say we end up with Na. No, this is not a super good one. Let's just do this. Calcium iodide. So we can track them a little bit better. Okay. All right. So let's say it becomes sodium iodide and calcium chloride. Okay. Let's say that was a reaction that happened. Okay. Well, let's write what actually happens. Where are our phases? This is aqueous. This is aqueous. Still in water, so it's aqueous. And also aqueous. So if we write this and then we complete this down here, what's this? This is still Na plus and I minus plus Ca2 plus and Cl minus. All right, so you see this and this, nothing has changed. Okay? So we could say these come in here and these swap, all right? And then we have a double replacement or double displacement, right? But if it starts out and they're completely disassociated, and then these are completely disassociated, Nothing has changed, so there is no reaction. Okay, so that's the basic thing about it. All right. So so the rule then, if we want to just kind of put in there, if both reactants and possible products are soluble, no reaction takes place. And that's it. That's really all you need to know. Okay? All right, now, what's much more interesting is what happens when something formed is insoluble. Okay, so what happens? All right, let's look at the examples he sort of looks at with us here. Okay, so we can look at 276 there, right next to the figure there, where he talks about yellow lead iodide, that picture. He says, when solutions of soluble compounds are mixed, if an insoluble compound can form and precipitate, it does. All right, so let's just copy down what he's got here and talk about it as we're doing so. All right, so what do we have? We've got lead nitrate. Okay, so just for our remembering, if we flip back a little bit to page 265, we can see nitrate there at the top, and we know it's what? We know it's a -1, and there are two of them, so he's got to be a 2+, right? Or a 1 minus and a 1 minus and a 2+, okay? And then what's our other thing? Mixed with potassium iodide. All right, note that he's also got them as aqueous. So we know these are soluble in the water. What's this? This is a -1 and a +1. Okay? I'm all over the place. Pluses and minuses go before or after. I don't even know. All right, we're wild. We're crazy people. We're putting our pluses or minuses wherever we want. All right? All right, so then if we look at this, we got PbI2. Okay, so we still, let's see, this is a +2 and a -1. These do not play into it. I'm just reminding y'all because we're fixing to get into finals review, and I want you not to forget about oxidation states. Okay? And KNO3, aqueous. Okay? So what I didn't do is I didn't tell you what the state of the phase of this one is, and I meant not to tell you this one anyway. So that's aqueous. He tells us that. All right, but if we look back, flip back to 265. All right, so what we could have done is we could have seen, look, we got a minus here, a minus here. These are likely going to swap places. Okay. All right, now if we were in the real world, we wouldn't know whether they do anything at all. We'd have to do a whole bunch of other stuff, but this is a chemistry problem that's given to us. So we assume that if there is an insoluble product, that this is a reaction that would go forward without us doing anything else, okay? So we're going to assume these swap places. So we could write this, and based on their oxidation states, just sort of say, okay, these are what I think is going to form. We're going to have a lead iodide and a potassium nitrate. All right, so let's look at potassium nitrate, or let's look at nitrates on page 265 there. All nitrates are soluble without any exception. Okay, so we know this is soluble, which means it's going to remain dissolved, which means it's going to be aqueous. Okay, so we check for solubility. Is it soluble? Yes. If yes, we know that it's aqueous, right? Because that's what aqueous means. It's dissolved. Now let's look at iodine. Okay, those are all soluble, right? Wrong. They're all soluble except for compounds of silver, mercury, and lead. Okay, which look, we have a lead here, which means that it was soluble, but that's an exception. So this is insoluble. All right, so that's like our red alert word here. So we know that he's going to be a solid, because that's what happens. When things are insoluble, they form a solid, and precipitate out. They are precipitates. You're going to have a lot of exclamation points, I can tell. All right, exclamation point kind of night, or morning, as the case may be. All right, so this one precipitates. So we know what we've got here. All right, so if the question was, what's the precipitate from this reaction? That's it. The one thing that's solid. All right. So now, let's come back in here, and this will transition us from here into our next section, which is net ionic equations and spectator ions. All right, so we're don't worry about that just yet. Okay, let's just focus on writing an equation that has ions. All right, so what are we going to have? We're going to have a PB 2+, we're just going to write them as ions and no longer as compounds. Instead of just writing them as aqueous, we're actually going to show them as their separate ions. Then we're going to have NO3, we're going to have 2 NO3s, and that's going to be a minus. All right, and then we're just going to break this one up. All right, we got it. Why did we have, oh, okay, we didn't balance it earlier. Okay, so let's go back just for a second. Let's balance this. We got 2 NO3s and only 1 over here, so let's put a 2 right there. It's going to give us 2 Ks there. We got 2 I's here and only 1 here, so this 2 is going to balance that. All right, so what do we got? Now we've got 2 K pluses and 2 I minuses. What's that going to go to? All right, so this is not an ion anymore because it's a solid compound that's dropping out of that solution. So we're just going to write that as PbI2. All right, and we can be doubly sure and write a solid next to it there. All right. Plus, we got our 2 Ks over here as pluses in solution there, and our 2 NO3s, those are minuses. Okay, so now, this is our ionic equation. Okay, so how do we get from that to where we need to be, which is our net ionic equation? Okay. All right, so let's review a little bit, just a vocab here. When something is the net, okay, let's say I make, let's say I make $1 million teaching chemistry. I'm being modest. I really make $2 million teaching chemistry. But just for discussion and ease of calculation, we'll pretend I only make $1 million teaching chemistry. Okay? But it costs me, whatever. It costs me $100,000. Right, so this is my gross income. These are my expenses. And so net, I only make $900,000. Okay, so net's what's left over after you take all the stuff out, right? They paid me $1 million. I had to spend $100,000, so I only netted $900,000. Gross minus expenses is your net. Okay, so that's what a net ionic equation is like. Okay, so this is like our gross ionic equation. All right, and what we need to do is we need to take out the stuff that's on both sides. Okay, what is... All right, well, let's go in a little bit different. In order to do that, we're going to talk about spectator ions. All right, so if somebody's a spectator, what are they doing? Well, they're not doing whatever they're watching, right? If they were playing basketball, they'd be a basketball player. But if they're a basketball spectator, they're watching other people play basketball, right? Okay, so spectator ions do the same thing. They're ions that don't actually participate in the chemical reaction. Now, they're important to deliver those ions into the solution, right? So think about it this way. If there is, often what will happen is you need to get some drug into somebody's body. Let's say their cholesterol medicine or their even something like aspirin. Okay, so aspirin is salicylic acid. Well, the reason it's salicylic acid is that it's a preparation that's been turned into a salt to make it dissolve in your body so that it can deliver the active ion, the salicylic part of it, to the places where it needs to go to stop you from having a headache. Okay, so it might be that salicylic acid might be hydrogen salicide, we'll call it, right? That hydrogen doesn't do anything. It just goes and binds with something in your body and just, either gets breathed out or excreted out somehow. Okay, but that other part of it, once it's an ion, is active now to do what it needs to do. Okay, so like if our goal was to make this, we got to get that iodine into solution as an iodide, as an ion. And we got to get that lead into solution. If I just took a chunk of lead and threw it in water, it's not going to do anything. Okay? So I've got to make a compound out of it, something that will dissolve that lead and get those lead ions into the water. And so that's what this is. Okay? So these spectator ions, the way we identify them is they are ions that appear on both sides of an ionic equation. Okay, so when we've written it like this, who do we see the same on both sides in an unchanged state? All right, so let's see. Pb2 plus, nope, he's locked up over here, so he's not a spectator. 2NO3 minus, 2NO3 minus. Okay, we're going to draw a little, let's draw little eyes for spectators. Okay. No, those glasses don't look very good. Sheesh. Okay, how about we just write spectator? Hey, there we go. All right, spectator. All right, who else? So now we'll call this a spec. All right, 2K plus, 2K plus. Spectator. Spectator. All right, so once we've identified the guys that are on both sides and the same, we can remove them. So we'll say identify spectators, remove them, and if that helps you to cross them out or do whatever, and then we're going to write net ionic equation without them. All right, so what does that mean? All right, so let's look right here. Let's take out all these specs and just literally write exactly what's left without those spectators. Okay, so we will write PB, 2 plus, and 2I minus goes to PB, I2 solid, And I think we're supposed to say aqueous and aqueous here. All right, and so then this is our net ionic equation. Okay, so we started out, we made an assumption about what the reaction would be. They'd swap partners here. We would check for solubility, see if something was insoluble. If it was, we would know that he was a solid. Then we would take our ionic equation and break everything up we could except for the solid because he's not an ion anymore. Oops, sorry, I'm off the screen there. All right. He's not an ion because he's not in solution anymore. And we'd rewrite it like that. Then we'd find all the stuff that was the same on both sides, get rid of it, and we would rewrite that as a net ionic equation. Okay? So it's pretty straightforward. You know, it's not super complicated, and once you sort of realize what's going on there, and once you realize that ions can sort of hang out in solution and not really participate, then that helps you understand what's going on here. All right, so I'm going to walk us through number 28 from the back of the book here. So when I try to assign it to you later, because I forgot we did it, y'all all write me an email all at one time and tell me that I've assigned you something that we've already done. I'm sure that's what I'm going to do. Because I'll be like, oh, that is a good problem. All right. So let's look right here. We got number 28. All right, so we have solution of Na2CO3 and CaNO3 are combined. Okay? So we need to look at this and we need to recognize that we've got some polyatomic ions here and we need to make some assumptions about what is going to happen right here. Okay? All right. So what's our guess? Our guess is that this and this are going to swap places. All right. So I'm going to guess that we're going to have this NaCO3, Na2CO3 plus CaNO3 going to. This is a plus 1, and obviously, so this is a minus 1. This is a plus 2. This is a minus 2, and this is a plus 1. All right, so we'll have sodium nitrate and calcium carbonate. Okay. And we have 2 of these, and we got 2 of those, so we're just going to drop a 2 right there to balance it. All right, so we're balanced, and we made product assumptions. All right, so we've assumed what's going to happen here. Now we need to check if anything's going to happen. It could be that all of these are soluble. Okay, it could be that all of these are soluble. Now we're told this is a solution, so we know these are aqueous and aqueous on this side. All right, so let's flip back to 265, and let's look. Let's look at our products, our assumed products. We know that soluble compounds are nitrates, and there are no exceptions. Okay, so what's that mean? Definitely soluble, no exceptions. So no matter what binds with a nitrate, it's going to be soluble. All right, and then we've got carbonate here as an insoluble. And the only exceptions are ammonium and alkali metal ions. This is not an alkali, this is an alkali earth metal. Okay, and so this is insoluble. It did not fit one of the exceptions, and it's in the insoluble one, so that's what happens. All right? So we wrote the balanced molecular equation. Now we're going to write the ionic equation. Okay, so what is going to happen here? We're going to end up with 2 Na plus and 1 CO3 2 minus and 1 calcium 2 plus and 2 nitrates minus, and that goes to, this is aqueous, so it's still floating around as ions. And remember that 2 is 2 of these and 2 of those, so we got 2 of these. But this is a solid, so it's not ionic anymore. Okay, and these are all aqueous. AQ, 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 AQ. All right? Now, we need to look at the spectators. Wish I could draw better. All right, so who exists on both sides? This guy, he's a spectator because he's the same over here. This guy, he's a spectator right here. Spectator. Okay? So basically, we can say Ca, 2 plus, and CO3, 2 minus, both in aqueous, and they go to form a solid compound that precipitates out as a precipitate. Okay? All right, so what's the pattern here that we see? We see that the thing that's the precipitate, the 2 ions that make it up, are the only things that are left in the net ionic equation. Right? Everything else just sort of spectates. Okay? So that's it. So we can identify the spectator, and if I asked you to write those down, we would say spectators are the sodium ions and the nitrate ions. Okay? Show up on both sides. They just watch while these ions get together to make that insoluble precipitate that comes out. And that's it. You can be asked any of 100 different compounds, equations, and they'll all act the same way. You'll do the same thing on all of them, and it'll all act the same way. You will use, I expect on your test, you will be given this table, okay, and you will be asked to perform these sorts of calculations, and you'll need to be able to look at those compounds and find their oxidation states, okay, and figure those out. So brush back up on that. Oh, and one other thing, we're about done here, but one other thing I wanted to tell you, one of the things I'm studying is this, right here. Okay, so often what happens when you pump water out of the ground, or even if it comes out of a river or lake that ran through calcium deposits or magnesium deposits, is that you end up having these things called hardness, and sometimes maybe y'all have been at a cabin or something, or been somewhere where they have sort of what's called hard well water, which means they got a lot of these dissolved things in there, and it makes soap hard to come off of your skin. So if you take a shower and you put shampoo in your hair, you just can't get it out very easily. And that's got something to do, we talked about saponification, and that, I think, was it earlier in this chapter? Maybe, yeah, earlier in this chapter. It interferes with that saponification deal where it latches on one side and the other, and so it messes that up. So you got to get that hardness out of the water, and that's called softening. And often you do that with lime. Okay, not limes, but lime. And so basically what happens is you've got these things in there, like this calcium carbonate here, okay, and you need to get it out of there, so you're adding the lime to it, and note this, what's it do? It forms an insoluble, ooh, a little vertigo there, exciting. It forms an insoluble thing, which you can then filter out, or it's called flocking it out when you add something to make it clump up and fall out of the solution quickly. Um, and so you can see that each one of these forms different solids that are then, so these are not written in the ionic compound, but that's what we've learned about today is exactly what you do to get things that are soluble in water out of that water. You add other things, you encourage them to go into those other compounds by making, doing it with the right way, at the right temperature, and all that stuff. And then those new compounds are insoluble in water and they drop out. And so you've sort of pulled those things out of the water. So I thought that was kind of cool because what we're talking about is exactly what is done, and this is the basis for how they do it. So anyway, that's going on at water treatment plants, drinking water treatment plants all over all the world right now, as they're pulling hardness out of water that makes it difficult to use. And yeah, so anyway, a little interesting fact there. Okay, well, y'all have a great day. Do your homework. And again, I will try to get those quizzes graded and back to y'all early next week so we can be prepped for our test, which I think is maybe the Tuesday after that. I don't have the planning document up in front of me. So, all right, y'all have a great day. Talk to you later. I've lost my mouse.